Okay, so let's get started. So today we are going to talk about nonlinear classifiers, and we're going to focus on. And I've got the volume on here again. So we're going to focus on the extension of the so the specific extensions of the types of classifiers we've been looking at so far. So we're going to take the two models we've looked at for the linear classifiers and show how to extend them to these nonlinear classifiers. And it's going to be like a more diverse way than the way we did this with nonlinear regression as well. There are a variety of ways to do this. We're going to, kind of see a few related options. And the nice thing about the things we'll cover in this lecture is that they're going to kind of inherit all the nice properties from the linear regression that we learned about and kind of fit in all the frameworks we talked about earlier in the semester. The next lecture, we'll talk about even more diverse ways of building nonlinear classifiers. But these are going to be the ways which kind of dominated the machine learning up until about 10 years ago, because they inherited all the nice properties. Okay, yeah, the Utah Data Science Day, you should all sign up for that. Just in the schedule, quiz. So 6 is happening today, right? So if again, you can have a chance to turn your cheat sheet. It will be on a number of questions. It'll be on the last 5 lectures, the 3 in clustering and the first 2 in classification. There's going to kind of be a lot of ideas in this lecture, and I'll put up front the ones that'll be kind of more likely to show up on the final in your homework, and we'll get into kind of more complicated things, a little bit harder to grasp, and it'll be harder for me to kind of test you on those things. But hopefully it'll build on a lot of stuff we talk about. And then the stuff on neural nets and decision trees, etc., will be in the lecture next Tuesday. This stuff could still show up on the final, so you can't just skip this material either. And then next week, Thursday, we'll do a kind of review for the whole semester. We will go through the practice exam I've linked off there. So great. Okay, and yeah, get started on homework 5. Due at the end of class, and the most. So because we got one of the early exam slots, we'll probably have trouble completing the grades of homework 5 before the final exam comes out. After you turn in, you have questions probably after the late deadline, which will be before the exam. I will, I'll be happy to discuss answers, but I probably won't post them online either. Okay. So let's get into it. I think there's a lot of stuff I'd like to cover today. We might not get to all of it because we have the quiz. For linear models, okay, the key element of this linear model was was going to be this. Was going to be the dot product. All right, and so the way this was defined was that we had 2 points, P and X, both in R. In RD, right? And so we defined that the dot product P dot X was this linear function. Or J equals 1 to D of Pi times Xi, right? So this was the basis of basically all of the methods we talked about so far in regression, like dimensionality reduction, kind of secretly embedded in the sort of clustering we did, although I didn't go over this, and like the linear models so far. They were built on, for data point X, we have some model parameterized by, so P, okay? So you can think of P as the model parameters, X as the data point we're evaluating. The key trick towards doing nonlinear classification is to kind of we're going to see just to change the notion of the dot product, replace this with something else. The dot product is kind of like similarity function. Okay, so that means that the more similar the points P and X are to each other, the larger the number should be. Okay, if there are two vectors, if we think of these as vectors, and we have, you know, a point P and a point X, you can think of them as vectors. The dot product is, assuming that they're like unit vectors, is kind of like the length of P dot X. It's kind of like the length of the projection onto P of X, right? So the more, if the length is the same, the more similar they are to each other, the more smaller the angle is, the larger the length of the projection is, right? If I make them so they're orthogonal, the projection is of length 0, right? So we're going to basically do is replace this notion of similarity with other notions of how similar are 2 points, okay? And the primary one, and so we'll think of this more generally as like a kernel. And the most common one is going to be, the Gaussian kernel. And we talked about this already with like the mixture of Gaussians. In this case, we aren't going to need, so if we have XP, we're going to write this as e to the power. We'll write this exp, so that's e to the power what's in the quantity, minus x minus p squared over, so sigma squared. When we talked about this for mixture of Gaussians, we needed some like coefficients and stuff, so it normalized to 1. We aren't going to have to worry about that here. Okay, so I'll just write it in this way. Okay, so this is kind of saying if I have 2 points, viewing this just in one dimension, let's say I've got x here, and I want to look at the kernel function, right? So this will be something like the kernel of x dot, so something for any value p. So if I have a value p, it's going to evaluate, you know, this is the value it's going to get. And so the idea is you take the distance between x and p, okay? This is the same as the normal distribution, but this is a multi-dimensional version of it. I look at the distance between x and p. The Gaussian, you square it, and you do e to the minus that version. So that distance gets bigger, these kind of drop off exponentially fast, right? So it kind of is rounded at the top, and then it starts dropping off exponentially fast as the distance gets bigger. But the closer they are, I use my Euclidean distance here, the closer the Euclidean distance is, the larger I get a score, the more similar those 2 points are. This is a different notion of, so similarity that's not based on angles anymore, but it's based on the distance between points. This seems a reasonable thing to, you know, a notion of similarity. You know, there are other versions of this. The Laplace kernel is defined instead. K of xp equals, again, the exponential, so e to the minus something, some distance, but instead it looks at this distance with some standard deviation, but not squared. So if I don't square it, what happens then is that your function looks kind of like this. So it's pointier at the top, and this tends to be a little bit more robust to noise, but it's less forgiving as you move away from a distance 0. Okay, so this is just another version. And then another important one is the polynomial, so kernel. Okay, and this I do xp, which is going to be, I start with the dot product, xp, some offset to some power r. Okay, so this is a little bit hard to understand why this is like a similarity. And in fact, it's, it's less intuitive in that sense, but this will allow me to kind of do everything I did with like polynomial regression, but with classification, if I use this kernel. And I'll kind of explain this a bit later. But this will allow you to kind of, if I were to expand this expression, right, I'm raising it to the power r, and I have two terms, the inner product and c, and if I expanded that to the expression to the power r, I'd get all the polynomial factors, and I can write down any kind of polynomial and up to degree r in this way. Yeah, question. That's x minus p. Yes. This is a minus. Yeah, so I'm looking at the distance. I'm using the norm of x minus p. So you take the difference between them, you look at the norm of that gives you the length. Yeah, that's Euclidean distance inside that. Okay. Yeah, so we'll come back to this polynomial kernel, but you can do polynomials under this manner using this trick as well. So okay. Okay, so these are when I do. What we're gonna do now is look at how we ran linear classification, the last two methods we talked about, gradient descent and the perceptron. We'll start with perceptron, and we'll see how we can replace the inner product with the kernel instead, and this will give us nonlinear classifiers without really doing too much extra. But we need to rewrite them and think of them in a slightly different way. Okay. So let's okay, so the key is to remember the perceptron algorithm. Okay, and so if you remember how this worked, you took this, we're assuming the data that there's no offset, and we just compute this normal vector, and we're starting with any data point, y1, x1 as as the initialization. Remember, we're computing this function, which is going to be y of I yeah. So w x of I, right? And if this is, no, hold on, we're just computing this function. Yeah. Right, so we're computing this function. If it's positive, then we're going to label +1 or -1, right? So then we're going to look at the sign of this function. Okay, and so we're going to start by guessing w as just one of the points. If it's positive, we just look at the x value. If it's negative, we took like the negative of the x value, and then we say, so repeat. So find some xi, so yi such that g of w of xi is going to be so not equal to yi. Okay, so that we've misclassified it. Okay, and then we're going to, for this one, we're going to update w plus yi, so xi. Okay, and we're just gonna repeat this process. Okay, so the key insight here is we're going to somehow so, you know, so writing for, so this G of X equals for, right, so for a new point, I'm going to use P to distinguish it from the X's. This will help some notation a little bit easier, right? For a new point we want to predict, we're going to write G P of X equals W of P, right? We're going to learn this W, right? And then we're going to evaluate it, and then we're going to check the sign of this. But the key thing I want to do is I want to rewrite this W has a particular form when you run this, so Perceptron algorithm, as I can actually write this inner product, I can observe that W is going to be equals to, it's going to be these alpha I, yi, xi, where alpha I is going to be the number of times I found a mistake with xi, so yi, right? So when I run through this algorithm, I need to find some case where this is true, where this prediction I made for xi did not equal the yi, the right label. So this is a mistake. Okay. Okay, and then I only update this W by adding on this yi, xi if there's a mistake. And so I can write W in the end. It has this particular form where it's the sum over these yi, xi's, where this alpha I, right, is basically a count. How many times was this added into the W? And that counts the number of times I found a mistake at this value. If I keep finding a mistake on this, I'm going to keep adding it. Most of them, the number of mistakes is going to be 0. So most of these are going to be 0, and some of them are going to be 1. A couple of them might be 2 or 3. Right? It's the way to. If I keep running it, and it's a really narrow margin, some of these values might get large, right? But in general, the number is going to be, so pretty small. So let me go and now rewrite this expression for W as the sum of I equals 1 to n of alpha I, yi, xi dot P. Okay? So I can plug in this way of writing W. This is the same. This is kind of based on this algorithm. I must have calculated it in some way. I don't know what these alpha i's are, but there's some values I found. And now this is going to, and I can actually factor out the sum. The inner product is a linear operator. And I can write this as alpha I, so yi, xi, p. Okay? So my function, okay, so I said the linear function I learned only has this W is in RD. There are only D parameters it can take. I learn these D parameters, I have my linear function. Okay, but the alternative is that I say, well, I can also write it in this form. Xi is a constant, right? Xi is a constant, that's part of my input. Yi is a constant. All I'm learning are the parameters, so alpha I. Okay, so here we have these alpha I are a vector in Rn. Okay, is an n-dimensional vector. But if I learn this n-dimensional vector, right, then I can actually I can express something in this form as well, right? As long as it's to get everything in this form, you need something about the vectors being like full rank and stuff like that, but anything that's useful, I would find in this way. Yeah.
Alpha I or all?
Yeah, great. So it's all of alpha. So thank you. Where alpha equals alpha 1 up to alpha n. Great. Okay. And in fact, if alpha I could be, if I think of it being all of Rn, it could actually be a value which is like negative. Now my mistake counter can't find anything which is going to be negative, but the yi's could be sometimes have negative values. So I can kind of find negative values here. I could combine these together, right? I could just write, in some cases, we just write this as alpha I in this way, where I could learn whether I want to make it so it's negative or not. So a slightly more powerful way. I couldn't find this with the perceptron, but maybe I could find this sort of solution. Okay, so we'll come back to this. How would I learn the alpha i's again? We'll come back to that a little bit later. But you can see that these are this is a slight generalization of this model. And the other super important thing about this, okay, is that I've isolated this, this inner product. Okay, before I said, okay, I have to learn the parameters of the inner product, but now the parameters I'm learning are outside of this inner product, and the inner product are only with the data points. P is my new value, and xi's are like all the data points. So one other thing I can do is I can replace with instead a more general function xip. Okay, so I could replace this with the kernel. Like I said, well, I want to find something in the form on the right where I have these alpha values I'm going to learn, but instead of using an inner product, I'm going to plug in one of my other kernels. It could be the polynomial kernel or the Gaussian kernel, and this turns out will give you a nonlinear classifier. Okay, what's cool is I just need to, if you look at this, I only need to evaluate G at P. I can do that in the form on the right with the nonlinear kernel, and because that's all I need to do in order to check this condition, if there's a mistake. I can run this mistake counter version of this by just checking this function using the form on the right here, right? So I can use this form on the right with the kernel, right? So I could write this as G alpha of P is going to be equal alpha I kernel xip. Okay, and maybe so I'm doing the mistake counter form. I'll put the yi's in here as well, right? So that I can just count the mistakes. So if I use this expression, right? So I can plug this expression inside the perceptron algorithm. Okay. So I can't quite do. In this step, you have to instead say, well, initially. So all I'm going to keep track of is instead here, I'm going to say that alpha is going to initialize as 1, 0, 0 up to 0, right? So I'm not maintaining this W anymore. I'm maintaining, this is instead getting alpha plus where the ith coordinate, I'm going to increment the ith coordinate is all I'm going to do in this alpha vector here, right? Okay, so I'm starting with I pick any one to be the initialization, right, up at the top. And then as I iterate, I'm going to evaluate this function. I can still evaluate the function defined in this way, check for mistakes. And then if I find a mistake, I increment some mistake counter. Okay, so I can run this perceptron algorithm with kernels. So this is the kernel version of the perceptron algorithm. And this is going to give a non-linear classifier. Okay, I want to try and show a couple of pictures on how what you're getting for like a nonlinear classifier. Okay, let me try and draw some examples here. So let's say I've got some positive points here, and so some negative points here, right? And so what I'm going to do is over the course of the algorithm, I'm going to select some of these as the ones which I'm going to say, these are going to be the ones that I have found mistakes on during the algorithm. Okay, let me pick some extra ones. And let's say we're doing it this with like the Gaussian kernel. And so what I'm doing is I'm kind of going to be having something similar to this point is going to get a large value, right? The Gaussian kernel is going to put a bump on top of it. As the distance decays, it's going to be dropping exponentially. So there's going to kind of be this kind of height function around here that is dissipating as I'm getting further away from this. Okay, and so so as I get further away, the height function is going down, and in fact, I'm going to get a negative value around these, right? These are going to give me some negative values. And so then there's some line which is where this crosses over from 0. These are positive values. These are negative values. And if I'm over in kind of this region over here, right, if I were to evaluate a point P, it's going to be much closer to the xi, the pluses, right? Remember, the cost is decaying exponentially. So if I get further away to the negative ones, those are going to have much less influence, exponentially less influence. So it's still going to be positive. It might be a small value, but it's still positive. And there's kind of going to be this line which is dividing through here, which I kind of drew here. This line is where the function value is 0. This is where G alpha of P equals to 0 is going to be on this line. So these are all the positive points. These are all the negative points. And this dividing line is not going to be, it's no longer a line anymore. It's a curve. It's a nonlinear curve. So I can fit these functions that kind of is like adapting to the data. Okay, and you can kind of, we're going to kind of go through this completely, but you can kind of imagine if for any point set, I could eventually find some function, this region does not need to be so connected, that correctly classified any point set as long as there weren't a negative and a positive point exactly on top of each other. Okay, you could make it so it's got these kind of really weird isolated bumps and stuff like that, and it could work where it classifies any point. So with this point, there's always going to be a margin. So kind of the kernel version of Perceptron with a Gaussian kernel is always going to have a margin. That means it will always it'll always converge to something. It'll eventually classify all of your training data correctly. Right. Okay, so this is kind of a picture. There's a more computer drawn one in the textbook if you want to see. Okay. Let me draw another example of, let me talk about polynomials as well. So let's go back to the polynomial kernel. Remember, I said you could define a kernel in this way: x dot p plus c to the power r. Okay, so this is going to give me all this. This is going to represent all so polynomials of x and p of power at most r. Okay, so up to, you know, so like up to a degree r. And I can do this by expanding this inner product with this c constant. That will help kind of govern the importance of the various coefficients other than the ones between x and p. It's a little messy to kind of see this, but I kind of want to show you a different way of thinking about this expansion. So, you know, so let's say I have, you know, a point, say P. I want to do what's called a polynomial expansion. And we kind of did an example with this when P was in R1, right? Then what we could do is we could map it to a value V in R plus 1, right? Where V equals 1 P squared up to PR, right? So this was if this was one-dimensional. But what if it's multi-dimensional? I just think it's important to kind of spell this out more clearly. Let's say P1, P2, right? This is P in R2. Then the expansion, we're going to do an expansion Q. So just a degree 2 expansion. We're going to do 1 px squared py squared, but you also need px times py. Okay, you need to think about these cross terms as well. Otherwise, you're not going to have quite as much representational power. Okay, you're going to get those cross terms by doing this polynomial kernel. Okay, so this is going to be a vector in R6. Okay, so what I can do is I think about fitting the coefficients to a vector in R6 here. And if I were to expand this polynomial form, I would see all these things that would have a c in front of some of these things, or a c squared in front, but then I'm learning coefficients and they can cancel with the c. But I need to have, you know, sometimes you just put a 1 there in place of the c. So I can do this expansion and I'm going to get this kind of polynomial space. If we go back to the one-dimensional example, I'll talk a little bit about how you'd actually run this as an algorithm, but just to think about this one-dimensional example. So P in R1, and now I'm going to think of having a some plus points here and some minus points here. Okay, there's no linear classifier in one dimension that can separate these points, right? I'd have to I want to cut here, but also on the other side, right? But if I do this lifting map, Okay, so I can represent all these points now. So I want to represent them as Q. Q is now going to be equals to P and P squared. There's also going to be like, there's a one term, but we can ignore that for this picture, right? So just represent every point as the value of P and also P squared. And so what I'm going to get is this, there's going to kind of be this, this underlying, so parabola, right? So if I have P and P squared, all the points have to lie in this parabola, right? So these points kind of are, the P value is the same, but the P squared value is given. So this is be the P squared value up here. Okay, so these will be the negative points, and these will be the plus points. Okay, and so now I can find a linear classifier in this space. Once I've done this variable expansion, this lifting to this polynomial representation, this I can now find linear classifiers in this space, but these map to nonlinear classifiers in the original space. Okay, so by doing this polynomial kernel, you can think of mapping it to a higher dimensional space, and then I can find linear classifiers the same way as before. Okay, if I go back to this expression, so if I think of this mapping, this kernel as kind of like some sort of thing that's fixed, I'm again fitting a linear model here. I'm just learning a sum of linear things times some sort of kind of fixed quantity, right? So I'm still kind of learning linear models, the same techniques as before, but I'm kind of transforming the data in a nonlinear way in some space where then I map the points into that space where then I can find some linear fit. Okay, with polynomials of so degree R, this is limited. I can kind of control how much the expansion is going. I'm getting more and more dimensions. I'm mapping the data into a higher dimensional space, and the hope is you can find linear classifiers in that space. And so, in fact, there's an algorithm so you can think about. So the first way of doing polynomial classification, right, is to do this polynomial kernel with the kernel perceptron. Okay, do the kernel perceptron where the kernel is the polynomial kernel, and that will work in this way. I will get a classifier that might implicitly look like this, but now I can do I can also do polynomial classification via so this like lifting. Okay, so the polynomial classification with lifting is so what I do is so step one, for all xi in x, I map to q in R. Forget what the the general dimension is here, but it's it's going to be it's something like d roughly d times R dimensions. Okay, so there's some higher dimensional space. I'm doing this polynomial expansion, right? So I have like 1 x1 squared, and so so forth in this higher dimensional space. Okay, and then I this is qi. Then I build a so linear classifier on now qy. right? So the Q now lives in this higher dimensional space, but I can build a linear classifier here, and then to apply to new P in RD, I first need to 3A, and this will be a function from R that's like O of D times R to to the reals, and so I'm going to find this function, and then for 3A I'm going to map P into this higher dimensional space. Okay, and then I'm going to check the sign. Take the sign of G of, let's do Q of P. Q of P, so evaluate it in this space, right? So I first transform my data, and then on a query, I also have to transform the query, but I can then build linear classifiers, but they will on this polynomial expansion, in the original space, it'll be this nonlinear classifier. It's kind of a similar trick we use with regression, but you can use the same trick here with kind of classification as well. Okay, so this worked with polynomial kernels. Can I do this with like a Gaussian kernel as well? Kind of. Okay, I have to get this explicit mapping in this high dimensional space for this to work. This requires mapping to this higher dimensional space. And I don't want to, I can't do that perfectly with Gaussian kernels. Okay, I can only, it turns out you can approximately do that. I can map it to like a 100-dimensional space, and it will work approximately like a Gaussian kernel, but not exactly like it. And as I get to I can do it to 1,000, there's a process, it's like a Taylor series or something. But if the higher dimensional space, the more it approximates the Gaussian kernel. And typically, 100 or a few hundred dimensional spaces works about very similar to like a Gaussian kernel. Okay, so there are kind of ways to do this with the Gaussian kernel, but it's not as exact as with the polynomial kernels. I can do an exact expansion. Okay, we have got, let me see, about 5 more minutes before we break for the quiz. Yeah, so let me say one last thing. Let's talk about support. So vector machines. Okay, so these are called SVMs. Okay, and so when I was in graduate school, these were kind of the new fancy thing that was coming out then, like when, like deep learning stuff is coming out now. These were all exciting. It was, yeah, so these are where where our goal is to learn a function g of alpha that we can apply to a point P of the form of I equals 1 to n of alpha I k of xi p. All right, so the goal is this. We're going to explicitly say we're going to just learn these alpha parameters, and we want to learn the alpha in Rn. It's an n-dimensional space, and we want to somehow learn these alphas, right? So one thing we can do is we can say for all on our training data, we can again create a yi g of alpha of xi, right, which is yi k of alpha I Yeah, each of these 1 to n, yeah, the alpha I goes here. Alpha I, comma, let's say z of j, yeah, xj, right? So there's xi and xj. Okay, for the zj we're learning, we're going to put the zj into our loss function, right? And then, the goal is to, so find the min alpha over the sum of j equals 1 to n of some loss function on zj. Okay, this loss function tells us how misclassified is the jth point. And what's interesting here is that we have xi and xj here. And so this, if we're computing the loss function on the training data, we have to compute these kernels. There are basically n squared of these kernel evaluations we have to make. We end up having to compute this inner product between each xi and xj, and you can pre-process this, compute these once at the beginning, and then there are constant values that you can train on. Okay, so this runtime scales quadratically now in the size of your data. So it's a bit slower runtime, and this was a big challenge for a while. How do we get down this, runtime? But you can plug it into a loss function the same way as before. Okay, once I do this, I can create the ZI values, which tells me how misclassified. Remember, how classified. And I can use a hinge loss or like a logistic loss here. And I can deal with, even if it's not perfectly classified, that might be a better model than otherwise. But I can use gradient descent now because the kernel values are constants. I don't need to worry about the gradient of the kernel values. It's just a linear process. So the gradient descent is actually not too hard to derive and to optimize. As long as the loss function is convex, everything is convex. Okay. Typically, support vector machines say, I'm going to have a subset S subset X. These are going to be so support vectors. Okay, if you remember this, say this example here, I had a bunch of data points, but I only needed 4 to define a good classifier. If we run the Perceptron algorithm, it's gonna terminate, it's gonna have t equals 1 over gamma star, the length of the margin squared steps. So after that many steps, I only need non-zero values for these alpha i's in this many spots. This might be a small value, right? So I don't need to build a classifier to optimize this on all of the data points. I don't need to use all kind of n here. I can just say, well, if I just have this, these support vectors, and let's say the support vectors, the size of this set is k, well, then I can build my model instead. G of alpha p is just the xi in S of size k of these alpha I. Okay, if I can select those, then the number of things I need to, then if I look at these xi, xj, they're only going to be k times n things I need to evaluate, if I know which ones are going to be interesting. So I can choose the subset of points which are useful either through like stochastic gradient descent or through the Perceptron algorithm, and then I can optimize them with gradient descent. And this was like what support vector machines are doing. Or I could run the gradient descent, and some of the alpha I values are going to be really close to 0, and I just round them back down to 0, and I drop those parameters. And I get a simpler model, and it's more efficient to compute. So this is kind of the idea behind the support vector machines, which are extension of this. Okay, we should stop here. I told you it was going to get kind of complicated towards the end, but hopefully you got the main idea that you can just replace the inner product with the kernel, and then you get these nonlinear classifiers, and it just plugs right into Perceptron, or you can expand them with the polynomial expansion and redo linear stuff. Okay, those are the main takeaways, but there's a lot more cool mathematics behind it. But we'll stop here for the quiz. All right.